Okay, this second simulation is Physlit Quantum Physics, and there's lots of different things within this website you feel free to explore, but in particular I wanted you to look at this. And what I like about this is that we have the quantum state on the right. You can control it with this n value up to 5, and on the left it's showing a ball that's oscillating back and forth on a spring. So let's first look at the position. So if I look at my position graph here, the one downside is that it doesn't really zoom well on the x-axis here. And note that the scale here doesn't necessarily match this picture. But so the key is that if this is going to be basically a classical probability distribution for position, so probability distribution here, position on the x-axis, why does it have this shape? So the general shape is kind of a U shape. So the least probability is occurring here at our equilibrium position. That's where it's going fastest. And then you have greater probability as you go to the ends. And so the idea being that it's spending more time at the end than it is in the center. Again, sorry that the scaling is terrible on this. So the idea being that the shape is due to you being more likely to find the ball at either of these end positions because it spends more time there. It's going slower. So then let's look at the correspondence principle. So we should see a similarity between the quantum probability distribution and the classical probability distribution, at least for high enough energies, maybe not for the ground state. Now, let's look at the position graph. So now, honestly, the prior simulation, we were also looking at some probabilities, right? This is basically just probability. And for whatever reason, it changes the scale when you do it this way now. And so it doesn't look exactly the same. But notice here that you still see that curve. And in the PhET simulation, we looked at this as well. So for the probability density distribution, I would say that the correspondence principle holds, that as you get to higher and higher energies, the dominant feature is going to be this U shape rather than the details of where those spots of zero probability are. So for high enough energy, we do see a correspondence between them. So the last question on this simulation was whether the expectation values of momentum and position agree between the classical and quantum systems. Now, while it does show us our expectation value for the quantum system, which is 0, on average, it's in the center, it's symmetric. We can switch to momentum, and it's also 0, because again, it's symmetric. But notice that over here, we in fact are not seeing any sort of, I mean, there's this velocity graph here, but we don't actually see what the expectation values are. But on average, right, the distribution of it moving to the right, what those velocities look like versus the velocities moving to the left, on average, it's traveling 0. Right? If you integrate over a long enough time, it isn't on average going anywhere. And the average position, expectation value, is again right in the center. And so we see that the expectation value of our classical and our quantum systems do correspond. And again, that is something that's kind of coming from that correspondence principle, that on average, as long as you consider high enough energies, you do expect to see some agreement. So that was just the goal of this, to again think a little bit about how our quantum and classical systems are similar, but also how they're different.